Yeah, so I think, should we just start with the homework
Yeah, I
and
think that's
start
better
from
if
the
we just start
problem
with the homework and
sets?
then we could do the test after. So I feel like it's better practice.
Okay, so I have problem set 1 here. Let me zoom in more.
You have to record or
Yeah, I'm recording already. So,
okay.
um, okay, so problem set 1, pretty simple one. 64-bit system, provide the value of PCA for each during execution if OS loads the program offset 82. So it's 64-bit. So if it's bits, you always have to divide by 8 to get the amount of bytes to increment by. So 64 divided by 8 is 8. So that's how much it's going to increment by every time. And the first line of the code is the offset. So 0082. And then plus 8 is 0090, 0098, 0106. Oh, a little bit. 6. Then plus 8 is 0114, 0120. And actually, there's one more time after the fetch stage that the program counter increments. So technically, the program counter at the end will be 0128. Okay. He didn't really ask, but this is an L type, right? Also an L type. Branch. This is R type. Also an R type. And this is an S type. Right? Does it look right?
I don't even have my iPad with me. I don't even know if I could check. But it
Okay. I
looks right
think I
so
have
far.
the solution set. Let's see. Is this the same one? Let's see. 2082, 90, 98, 106, 114. Oh, oops, did the math wrong. Definitely don't do the math wrong in the exam. 1, 2, and then this should be 130, right? Yeah, he didn't write it, but technically the program counter goes to 10130. He didn't mention anything else. Okay, so ignoring my really bad basic arithmetic skills, that's fine. Okay, problem set 2. Provide type of instruction and all the stages for each of the following instructions. So this one, L type, L type, L type, branch, R type, R type, and S type.
When he asks for all the stages, does that mean we have to list like fetch, decode, exec, mem, like that? Is
Yes,
that what he means? Okay.
yeah. So for L type, it's fetch, decode, exec, mem, um, and write back. So same thing here. Branch is fetch, decode, exec. R type is fetch, decode. Every single and every single instruction always has at least fetch and decode. I think it's like what jump has
Mhm.
fetch and decode. Branch has exec because you have to do the comparison. Um, for R type, you don't have to go to main memory, so that's definitely not that. So it's just exec and write back. I think that's what it is. For S type, it's fetch, decode, exec, mem. There's no write back. Do we know all what each stage means, or
Yeah. I was gonna send something that would help us. Let me see if I could get it. Because if I send this, if everybody prints this out, I think everyone should be fine. Like you don't even have to memorize it. Let me find it.
okay? Well, while that's happening, the total memory reference count for the above execution. So total memory reference count is how many times you have to go to main memory overall. So every time you do a fetch, you have to go to main memory because you're fetching the instruction, and all the instructions are going to be in main memory. Um, but you have to like look at the code as well. So for this code, this one is definitely going to run once, and this, but then you have to check for this, the branch not equal. Um, we don't actually know what's in register 1 and register 2. We just know that they were like loaded with data from those addresses. So it could be that they're equal, or it could be that they're not equal. So um, so yeah, if it's 1 1, this could be either 1, or you could have 0 time. Well, actually no, you still fetch it, and then you could jump here. So actually what could happen is you could skip these 2 lines if you jump
Mhm.
to here. So this one will definitely
I
run.
also sent the screenshots if because that makes it like easier,
Let's
probably
see.
for everyone. As long as you print that out, you should be good. It tells you everything, like literally everything. I don't think it misses anything.
Let's see. Load instruction. Yeah. Oh, it doesn't write back. Add instruction R type branch. Okay. Yeah. This looks right. But I was just wondering, like, what happens if, like, you know how sometimes he does let's say R1, right? But then he loads
Mhm.
like a value, not an address. This is an R type instruction, right?
Um, let's see. Yes, it is.
But then
Because it's
does
like
this go in the ALU? Do you know? Or is it just like directly loading it into this register? Because you know, usually when you have like a R type, it's like usually like, oh, you do like, I don't know, R1 plus
mm,
R2, right? And then
yeah.
this goes into like one part of the ALU, this goes into the other input of the ALU, and then it goes out the
Mhm.
Z register and you put whatever's in the Z register here, right?
Yeah, that is confusing. You think like that value goes straight into Z?
Yeah.
Like it's
We
just
might
it
have to
just
ask
gets
Vivek, because I'm
yeah.
not really sure. Did he ever mention that?
He never
I
went in
don't.
depth with it because I don't think it can't be a load. It makes no sense
Yeah, it's
because
definitely
load
not a
is an
load.
actual.
In this class, it would be an R type. I'm just not
Yeah,
sure if
it's
it's
not a store either. Can't be a jump obviously. It's
yeah.
R type, but it's like I don't know like the steps for it specifically. Fetch is fine. Decode, I guess. Yeah, someone has to ask him. I don't
Mm.
think he's gonna put all that.
Yeah, I mean, who knows? It's Vivek.
Yeah, that's true.
So, okay, so it could be that all 4 of these lines execute, or all 6 of these lines execute, right? Um, so it's either 4 or 6, right? Um, well, or 6, but um, we have to add the amount of times you have to go to memory for any L type or S type instructions, which is the first line, the second line, and the last line. So it's either 4 plus 3 or 6 plus 3 for the total memory reference count. It could be either, but we don't actually know what's in R1 and R2, so we can't say
Oh, he
definitively.
doesn't want us to like execute it until like the exact.
I mean, if he had like a situation where we knew what, like, you know how sometimes he's like, oh, assume every
Oh, he
address
gives us,
is valid.
yeah.
Yeah, if we had that, then we could give like a definitive answer, but it's literally like this or this is what we would put down if he asked it like this without like specifying.
That makes sense.
Yeah. And then data memory reference count is just how many times you go to main memory for data, not instructions plus data. So that's just three because it's the first line and second line, which are loads, and then the last line, which is a store. So that's just three. And then provide the total execution time given following stage execution time. So basically, I think he literally wants us to do like 40 plus decode is 10 here, plus 15, plus 30, plus 10. And then it's the same thing here. And then this one is literally just only 40 plus 10 plus 15. This would be 40 plus 10 plus 15 plus right back is 10. And then the last one is 40 plus 10 plus exec is 15 plus mem is 30. And I think it's okay if we don't add them up because he'll just take off points if the math is wrong, I think. So we can just leave it like that. So if I double check, it should be correct.
Uh,
Um, let's see. L type, L
math
type,
should be correct. I mean,
match.
either way, that's easy
Six
because you
plus
don't have to
five.
really add it, so it
Yeah,
should be fine.
yeah. So 6 plus 3 or 4 plus 3. This is 3. And then yeah, just just add whatever it says, depending on which stages those instructions have. Okay, so problem set 3. Um, for the following program, executing on a single cycle processor, can assume that each memory location contains value equals 2, and each register, if not provided, is initialized to value 1. Okay. Um, so for this on the side, I think it's better to just like write down um,
Hmm.
all memory addresses that are not specified have value of 2, and all registers that aren't specified have a value of 1. Um, okay. So then provide the total instruction memory reference count for the above execution. So how many times we have to go to main memory. Um, so we load R3 with the direct value of 600, it looks like. So write down like uh, R3 has 600, R4 has 0, R5 we're loading whatever address R4 is equal to, but we know that R4 is 0, so it's actually replace R4 with a 0 here. So we're going to address 0 and getting the whatever data is there, and then that's what we're loading into R5. Um, since we weren't given a value for address 0 in main memory, that means it's defaulted to 2. So that means that R5 is equal to 2. R4 is going to get R4 plus R5. So we know that R4 has a 0. We have known that R5 has a 2. So R4 equals 2 as well. And then, oh, did I do, oh, no, okay. And then R6 got It's another one of those whatever's in R2. Um, we didn't put anything in R2 yet, right? So that means it's a default value of 1. So we have to go to address 1 in main memory. And I don't think we stored anything in address 1. So R6 is also a 2 because anything that wasn't specified has a 2 in it. And then R4 gets R4 minus R6. So R4 equals 0 now. And then,
It equals. Does it equal? Oh,
yeah,
it
because R4
does.
is
Yeah.
2 and R6 is 2.
It's two.
So 2 minus 2 is 0. And R3 gets R3 minus 1. So R3 has 600 minus 1. So it's 599. And then we have a branch. So the branch is if R3 is equal to 0, then we go to the loop. But there's a bunch of bogus basically over here. Because, right, so this is loop, but we don't really care about anything that's happening except this line, really, right? Because it's just subtracting 1 every time. So this will finally exit once this goes from 599, 598, 97, blah, 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 down to 0, which is going to happen 600 times. So this is going to be, let's see, memory reference count. And oh, it's just the instruction memory account, not everything. So it should be 2, because these two lines only run once, right? So that's 2 plus 600 times, what was this, 1, 2, 3, 4, 5, 6? 600 times 6? Yeah, I think that's how many times these instructions will be run, right?
Let me check. Actually, I'm not even sure. It says here 2 minus instruction 1 plus instruction 2.
2
I have
plus
no idea what.
instruction 1.
2
What's
minus
it?
instruction 1 plus extra instruction 2. I don't know what that means. So
Let me see.
weird.
Let me see how you wrote it. Oh, I see what he means.
Oh, it's
So
just
the instruction 1 and
referring to
instruction
2.
2 runs that's 2 times because
Hmm.
this one runs once and this one runs once, like I said. And then since those lines run 600 times, that's 6 lines of code times 600.
Hmm.
And then yeah, he did the math out. It's like 3600 plus 2. So yeah, that's right. Okay.
That's good. I mean, we don't have to
Yeah.
really do the math, so that's easier for
Yeah.
us.
Yeah. Technically it's 3602, but I would just leave it like this, honestly.
Hmm.
Um okay, so data memory reference count for the above execution. So we don't care about this or this because you're not going to main memory for data. You are for this and this line. So that's over third, fifth line. Um, that's the only times you go to get data from main memory. So these two lines will run 600 times. So it should be 2 times 600. Provide the total number of cycles for above execution. Um,
Oh, it's the same thing. 3602, right?
is, um,
I don't know.
yeah, so because yeah, one cycle is per line, right? Like every line is one cycle in the processor, and then
Mhm.
those cycles are made up of the stages, right? So yeah, I think it still should be 2 plus 600 times 6, right?
Mhm.
Is that right? Yeah, okay. And then, okay, provide
Did he ever
CPI.
explain CPI?
CPI, I
Because
don't even know.
I remember
What does it
doing it. I
stand
just
for? Do you remember?
cycles per interval.
Oh,
Oh, something cycle
cycles per
Instruction, I
instruction.
think. Yeah.
Oh, machine. Close enough.
cycle,
Um,
cycles per instruction.
I
Um,
just remember I took
for
this
a
test once.
single, if it's a single
And
cycle processor, isn't it just one? Because every every instruction is only
yeah, every time
one
they
cycle.
ask that, it's always one. Like the answer is always
Yeah.
one. Even on the test when I took it, the answer was one.
Oh, oh, he did it like this. Okay, that's the formula.
Mhm.
Okay. Um, let's see. Oh, what even is that for? Total cycles divided by total executed instructions. Oh, okay. I guess in a multiprocessing computer, it would be different. Um, but for a single cycle processor, I guess it would just be one. Because he said it can get lower than one once you have like multiprocessing, I think. Did I write
Mhm.
that in my notes? I don't even know. PPI? I don't even know how to write this. It's like not related to like anything. PPI equals total cycles divided by total executed instructions. Okay. All right. So this one. That's all of that, right? For that problem set. All right, problem set 4. For this program, provide the memory reference string. You can assume that each memory location contains value 2, and each register. What happened to my cursor? That every register has a value. Same thing as before. Okay, so the memory reference string is going to be anything with brackets, basically, right? So 2, comma 5, comma 7. Okay, so this one is R4. So in R4, right before we loaded whatever was in address 7 on main memory, doesn't look like we ever stored anything in address 7, so we can just say it's default of 2. So this is actually R4 is loaded with whatever is in address 2. And then this store, so this would be an 8, 2, 6, and 4. So that should be the memory reference string. Let's double check. 25728 264. Yeah, okay. Okay, part 2. Assume a system with direct mapping of size 4. Okay, so the cache Cache size is 4, right? Size is 4. Complete the following mapping chart for each memory access and provide total memory access. Okay. The memory reference string is this. The cache has 0, 1, 2, and 3. And for direct mapping, it's the memory address divided by, oh no, sorry, modulo, size of the cache, right?
Yeah.
Okay. Memory address modulo size of the cache. Okay. So the first one, it's, what does he have this top box for? Do you know? Or this top row? Or,
I
I
would
think it's
believe,
to write the
oh,
string.
oh yeah, okay. 1, 2,
yeah.
3, 4, 1, 2, 5, 1, 2, 3, 4, 5, 2, 1, 2, right? Okay, so one mod 4 is just 1. So we put 1 here, right? 2 mod 4 is 2. Put 2 here. Let me clean that up. So 1, 2, 3. 4 mod 4 is 0, so 4 goes here, right? And then 1 mod 4 is 1. But if it's already here, we don't put it again, right? We only put it if it's getting replaced, I think, right? I think 1 and 2 are blank, but then 5 mod 4, which is 1. Now we put a 5 here, I think. And then a 1 again. 2 is fine, 3 is fine, 4 is fine. Put a 5 again here. 2 is fine, 1 here, 2 is fine, right? And then, okay, so these are all misses, right? Miss, 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 miss. This was a hit, this was a hit, this was a miss, and a miss. Hit, 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 miss, hit, miss, hit. What's the formula? I wrote it somewhere. Okay. So it's number of hits times the TC plus number of misses times TM plus the penalty, right? Time for the miss plus penalty. Alright, so how many hits did we have? We had 1, 2, 3, 4, 5, 6, 7. So 7 hits. Misses 1, 2, 3, 4, 5, 6, 7, 8. 8 misses, right? Okay. So 7 times 35, because 35 is provided here. Or no, oops. TC is 4. Okay. Sorry, 7 times 4 plus number of misses 8 times TM 35 plus 0. And we can just leave it like that. Is that right? 7 times 4 plus 8 times 35 plus 0. Yeah, okay, cool. Did I fill out the chart right? 1, 2, 3, 4. 5, 1, 5, 1. Does he want us to fill out the entire chart? Or can we just leave it like this? Because I've seen like a previous one where people just left it like this.
I mean, he highlighted it for a reason. I guess he's just doing it to show the work, right?
Yeah, I'm pretty sure we could just leave it like this.
Yeah, it makes sense to just leave it.
Yeah, because it's like too hard to read otherwise. I feel like. Oh, there's one more part. Okay, so cache again, but fully associative with least recently used replacement. Complete the following mapping chart. Okay, so again, 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5, 2, 1, 2. Cache 0, 1, 2, 3, right? So for fully associative, we just put whatever's the first available, right? So 1, 2, 3, and then 4. 1 is a hit. And 2 is a hit. 5 is a miss. So the least recently used. Okay, so if we had like, I think it's better if you just write like this, right? What we've used recently, and then we used 1 after we got this hit, right? So then we can cross this out and put it in the front here, and then same thing for 2 right after. So then we can move 2 to the front here, and then now the least recently used is 3. So we replace this with a 5. Then we can put a 5 here and cross out 3. So then after that, it's a 1 again. So we can cross out this 1 and then put it in the front here. Same thing with the 2 for this one. Cross out 2 and put the 2 in the front here. So this is getting kind of messy, but right now it's 4, 5, 1, and 2. And we're at this part right here, right? 3 is not in the cache, so cross out 4, and then put 3 here, right? And then we can put a 3 in the front here. And then now we're at this one right here, 4. What was not in the cache? So cross this out, replace it. Oh, did I put that wrong? Oh yeah, I did. Shit. 3 should have gone here, right? Yeah, 3 should have gone here. And then 4 goes here, right? I confused myself, fuck. Um, I think that's right. Yeah, and then we put a 4 again, because we just put this here. And then 5 is not in the cache. But the 5 over here, no, yeah, so, yeah, where 1 was. So 5 here, 5. 2 is a hit, so cross this out. Put a 2 here. 1 is a miss. So put 1 wherever 3 was. So put a 1 there. Cross this out. Put a 1. And then 2 is a hit. So 4, 5, 2, 1. Cross this out and put it in the front here. Right? That was really confusing. Did you guys follow that or no?
Yeah, I got it. It was just like you put instead of indexing 0 to 1 or 0 to 3, you just put 1 to 4. But I got it.
Yeah, it's basically because it's like least recently used. You
Yeah.
have to keep track of like what was not used. So if you when you had like the beginning, it was like 1, 2, 3, and 4, right? Because they were all misses. And then when you have this one here, that's a hit, but it's now it's been used. So you have to like move this to the front. It's like a queue basically. If you did that in like 313. And then the same thing with 2. So then 2 went here. And then 5 was a miss. So it's like, okay, well, I have to put the 5 in the cache. So I put it wherever this 3 was. And 3 was on this row. So that's why I put the 5 here. And then you cross out this 3 and put the 5 there. And then, yeah, 1 is in the cache here. So cross that out and put it here. 2, same thing, cross it out, put it here. So then you look at because the cache size is 4. That's why it's a little bit confusing, because it's like messy. You have to like know that like, oh, these are still in the cache right now. When you get to 3, 3 is not in the cache because it's 4, 5, 1, and 2 in the cache. But 4 is the oldest one, so you can cross out 4. Put the 3 wherever the 4 was, which was this row, and then put the 3 here. Now 4 is not in the cache because it's 5, 1, 2, 3. So you cross out 5, put it 4 wherever 5 was, which was this row. Put a 4, and then 5 is not in the cache. So then you put it where the 1 was, which was this row. And put the 5 here. 2 is a hit, but then you have to move it to the front. 1 is not here because it's 3, 4, 5, 2. So put it where 3 was, this row. Put the 1, and then 2 is a hit. So you can put it here. So the final thing is 4, 5, 1, and 2. Okay. Yeah. LRU is really, really fucking annoying, I think. So how many misses do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 misses. How many hits? 1, 2, 3, 4, 5, 6. 6 hits. And the formula is there in the upper right corner. So number of hits, 6 times 4, TC, plus number of misses, that's 9, times TM is 35 here, and penalty is 1. Okay, I think that's right? 6 times 4 plus 9 times 35 plus 1. Yeah. 1, 2, 3, 4. And 5 goes there. 3 goes there. 4, 5, and 1. Yeah. Okay. Do you guys know a better way to keep track of LRU? Or I feel like that's like probably the easiest way, even though it's messy. But if you guys have like a better way, I don't know.
Honestly, that looks pretty good. But I had a question of like go into a different topic. Like in this case it's LRU. You're using like a queue way to like sort it. But
Yeah.
what about least frequently used? Would you use the same idea or?
It's like similar, but you'd have to like keep track of something.
I
But if
remember
it
him
was like,
talking about it, but I just wasn't sure how exactly he wanted to do that.
yeah, so basically I would do it probably like something like this, maybe 1, 2, 3, and 4, and you tally it. Right. And then you
Oh,
have
you
a
had to
1
tally,
here
yeah.
when you hit here. So then it's like, okay, 2, and this one's a hit. So do this. And then now 5 is not in this, right? So we need to take out whichever is the least frequently used. But there's a tiebreaker here, right? It's either 3 or 4 will have only 1 hit, right? And he said then in that case it's FIFO. So this way I put it in FIFO in this order. So first in, first out. So this one gets crossed out. And then you'd put like 5 here, I guess, right? Yeah, cross this out and then put like a tally here. That was once, right? And then 1 and 2 also get hits again on these 2 columns, right? 3 is now not in the cache. So you do the same thing again. Least frequently, these both have a tie, right? 1 and 1. But at this point, what entered first? Oh, it was this one, right? So now you cross this out and then put 3 back with this. It's just a coincidence, I think, that
so far the LFU and LRU are the same. Because now you'll have like 4, and then 4 is not in this cache, right? 1, 2, 5, and 3. So this is a tiebreaker. Cross this out for yeah, and then 5 is gonna make a miss again. So then you cross it out here, 5 and 1, and then 2, another one here. Oh, but this time it missed in LRU, but in LFU it won't miss. It'll be another hit, and then another hit here. So that's how you would do LFU, I think. Just keep like a tally, and then I would just go down, and then like in FIFO, so if you have like a tiebreaker, take out like the topmost, whatever's tied.
Yeah, that makes sense. Thank you.
Mm-hmm. Okay. For following my reference string, cache supplies for total memory access time. Oh, he just wants us to do that whole problem set, but just without the boxes, or what? I don't know. Oh, he just wants the number of he just wants the TMA, right? The formula, but that basically you have to do that whole thing. That's kind of annoying. We just did direct mapping, and we just did LRU. I guess we could do like FIFO, right? And 2A set associative. How does it even do the solution set? This. Oh my god, he really does draw it. Okay, so let's do let's see. 1, 2, 3. Maybe I can just copy the thing from the previous problem set, right? I can just copy this. So it's 1, 2, 3, 4. 1, 2. 4. Right? Did I do that right? 1, 2, 3, 4, 5. Oh no, I missed a freaking 5. Okay. Okay, let's redo it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, it was just 1, 2, 3, 4, 5. Cache size is still 4, right? Yeah, okay, good. Okay, 0, 1, 2, 3. Well, fully associated with FIFO. Okay. So 1, 2. This is fully associative FIFO. So 1, 2, 3, 4, 5.
This is pretty easy, I guess, because it's just 5 will go here. And then, oh, 1 is going to miss. So 1. The 2 is going to miss. 2, 3. So since this is the cache right now, right? 4 is going to miss again. 5 is going to miss. Yeah. I think this just keeps on happening, doesn't it? Right. So I think it literally missed every single time, right? That was literally 0 hits and 1, 2, 3, 4, 5. Literally 15 misses. Did that make sense? I didn't really like draw it out, like filling it up.
No, it makes sense for me. It was pretty intuitive.
Yeah, you just pick whatever was like at the top,
Yeah.
but then you have to like just remember like the cache is up to here, so like this gets like deleted because once you put it here or whatever.
Mhm.
Whatever you put to the right replaces whatever was on the left, basically, for that row. Okay, so what is it? What's the formula? Number of hits, 0 times TC, which is TC is 3. Okay, so 0 times 3 plus 15 times, that would be, what's the penalty? Penalty is 2. Miss penalty 2, yeah. Okay, so that's P. Time for misses is 25 nanoseconds. So 25 plus 2. Okay. Yeah. 1, 2, 3, 4. That looks like what we did. 15 misses. Did he put the formula? Oh, did he not ask for it? Or what did he ask? He did ask, right? He just didn't write it down, right? Okay. He just didn't write down the actual numbers. But on the exam, if he asked for total memory access time, you would have to use the formula. Okay, so we can do the same thing, but with, what is this? Two-way set associated with LRU. Okay. Two-way set size. 1, 2, 3, 4, 5. Okay. So when it's a whatever way is how many the size of the blocks, right? Is that what it is? Like each cache block has a size of 2. I think that's what that is, right?
Yeah.
Yeah, each set has X amount of cache blocks per set. Okay. So every set's gonna have a size 2. So we have to split this into one and this into another, right? 0 and 1. I think that's what it would be, right? Because if you had, yeah, okay. Because one-way associative is blocks of 1, which is just direct mapping. But this is blocks of size 2. Okay. And then the formula is memory address modulo number of sets, right? And we happen to have one set, two sets. And then it's fully associative in that set. So 1 mod 2 is 1. So we put it in here, 1. 2 mod 2 is 0, so put 2 here. 3 mod 2 is 1, so it's this set. The 3 here. Same thing with 4. 4 mod 2 is 0, so put in this. Okay, so now 5 mod 2 is 1. So it's going to be in this set, but we have to do LRU. The least recently used was this one for sure. So put the 5 here. 1 will go into this set. The least recent used was this one. So 1 here. 2 is a hit. 3. That's going to replace this one. Is a hit. 5 is going to replace this one. 1 will replace that one. 2 is a hit again. 3 will replace this. 4 is a hit again. And then 5 is going to miss. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 misses. 4 hits. So it's just going to be 4 times 3 plus 11 times 25 plus 2 for this question. Is that right? 4 hits and 11 misses. Yeah. And does that look right? What we drew versus what he drew. 1. Oh, he put an extra row. That's so confusing. Maybe it's not. I don't know. I guess that's good, right? To have like another row to see which set it goes into. You didn't highlight it this time. It looks right though. I think. 3, 5. Yeah, I think it's right. It's just so confusing. This is just another of the same thing, right? I don't think we need to do it like again. Did we do every single type? We talked about LFU, LRU, we did FIFO, we did direct, we did set. Oh, I
There's
see it.
OPT, right?
Oh yeah, there's OPT. Yeah. Tara said, oh, I see if it's an odd number, it goes into set 1 and even numbers go to set 0. Yeah, for 2A, or sorry, for if the number of sets is 2, then that would work, yeah. But if you had like let's say your cache size was like 6, and it was like 2-way set associative, then it's mod 3. So it would work if the number of sets you have is 2, and that's the easy way to do it.
Do we have a question where he does OPT or no? No, right?
Yeah, I don't believe so, because he only said, I think he said it was only for benchmarking, so it wasn't that useful.
Yeah, but he might still ask something for OPT, which is like the annoying thing. I think my friend got OPT last semester, and he was like
Oh, really?
annoyed about it because he barely covers it.
With Vivek or a different teacher?
Vivek.
Hmm.
I'm just seeing if there's any OPT questions on previous exams. Yeah, you see, assume 2A set associated with hash 4 with OPT replacement. So there's an exam question with it. Okay, so we can do OPT now or later. What do you think? Oh, whoops,
I
I
mean,
just
while we're on
opened
it,
it up.
right?
Yeah, might as well, right? Okay. Um, for the following reference string, apply the OPT replacement algorithm. Okay, so this is four-way set associative with the cache size 4. So this is just fully associative all the way, right? Because the cache size is 4. 0, 2, 2, 3, 6, 5, 3, 3, 5, 6, 2. Okay, so definitely 2, 3, 6, and 5, because they all have to miss. 3 is a hit, that's fine. 4 is gonna miss. So we have to look ahead and then see which one is not going to be used, right? Where I keep this point. Do we look like whatever the cache size is spaces ahead? I don't
Yeah,
even
I believe
know.
it's the cache size spaces ahead, so it'd be, we would get rid of 2.
Yeah, because there's no 2 here, right? Because we
Mm-hmm.
do use 5, we use 3, we use 5 and 6. So, okay. So we put 4 here. Okay. And then 5 is a hit. 3 is a hit. 5 is a hit. 6 is a hit. And then 2 will miss. Okay. So now we're here. We look 4 spaces ahead because cache size is 4. We are going to use 4. We are going to use 5. We are going to use 6. We are not using 3, right? So let me put 2 here. So then 4 will be a hit. 5 will be a hit. 6 will be a hit. And then 7 will miss. So then we can look 4 spaces ahead. We're going to use 5. We're not using 6 or 2, right? There's a tiebreaker because we do use 4 and 5.
Mm-hmm.
And then if there's a tiebreaker, just do FIFO. Which one came first? 6 came first, right? So 6 can leave. 7. So then 5 will be a hit. 1 is gonna miss. Um, We're using 4, we're using 5, so it's either this or this again. That's a tiebreaker. Take up whoever came first, so that's this. So put 1 here, and then hit, right? So we had 1, 2, 3, 4, 5, 6, 7, 8, 8 misses, right? How many hits did we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 hits? Is that right? Okay, yeah, that was 19. Okay. So it's number of hits, 11 times. Wait, main memory access time is 20 now. So, oh, cache access time. Okay. So if it's a hit, then we take this one. So 11 times 3 for the hit. Plus, there was 8 misses. So that's times the time to access main memory, which is 20, plus the penalty, which is 1, right? Do we have to also include looking at the cache for no, no, the penalty is only when you miss, right?
Yeah, we only get a catch penalty when we miss.
Okay. I think this is what it should be. Which question was this? It was this one, right? 2, 3, 6, 5, 3, 4. Yeah, I think it's this. Okay. 4, 2, 6, 5. Yeah. Okay. Looks like it's right. And then, yeah. 3 nanoseconds times 11 plus 8 times 20 plus 1. Yeah. Okay. Yeah. Okay. So for OPT, basically, you have to look ahead for however many the size of your cache is, right? And then see which ones you do use that are already in your cache. Because you want to make it so there's as few misses as possible. Okay. Um, okay. 3 processors, their caches. There's 3 processors with individual caches. They're connected via bus. In the initial state, memory location X has the value 5. And the caches are empty. Did he accidentally fill it in? Or did I fuck up? Oh yeah, they're already filled in. They shouldn't be filled in. They should have been blank, right? Well, I guess we can just like talk about it, right? So technically, like this would have all been blank. Um, um, okay. So for line 1, we do a load of whatever's in address X to R1 on processor 1. So whenever we have cache, we have to use it. So this is a read miss. So just update the cache with it, set it to exclusive. So that's what happened on line 1. On line 2, we check for on processor 2 if we have the address in the cache for processor 2. We don't. So that's a write miss. But when we have a write miss, it says do not allocate. So we don't have to bring it from main memory. But then when we write, we have to send the invalidation bit to anyone else that has X, and processor 1 has X. So that's why this gets invalidated here. Because when processor 2 has to write, it also has to send an invalidation bit to for the other caches to snoop. Okay, line 3. It's another load. Oh, yeah, this has already been updated to 8. So then no other cache has it because this is invalid. So it's basically as if it's not there. So this is set to exclusive. And then processor 1 wants to read it. The other cache is Snoop. Cache 3 has it, so then it shares it with cache 1. So then cache 1 and cache 3 have it. It's set to shared. And then processor 2 does a write. It'll be a write miss because it's not in cache. And then it'll send the invalidation bit just like the other line. So then these two become invalidated. I'm still a little bit confused on write through versus write back. Like, for this
Isn't
question, did
write
it
through
matter?
when it
No, go ahead.
isn't write through when they updates both the cache and memory at the same time, and write back is it only updates the cache and memory sometimes in some cases.
Yeah, the memory is only updated for write back when you need to,
Hmm.
which is why in write back you'll have modified state, right? But then in write through you don't, right? Because there's no point of keeping track of modified state if you're always updating both.
Yeah. Hmm.
But then why didn't we have a like in what situation do you even get like a modified state for write back? Because it didn't happen for these lines of code in the first question.
The only thing I could think of is if we had an allocate instead of on do not allocate on write miss. I'm not exactly sure if that's correct. Let me think.
All right.
In what situation would the cache have something newer than? Oh, okay. So, I mean, yeah, you have do not allocate on write miss, but you could still bring it to the cache if you have a read miss, right? Because like do not allocate and allocate only they matter for writing, like store type instructions. So basically, if you did like a read, or if you did have no, I don't even know for allocate on write miss if you would have it, right? Because wouldn't you immediately overwrite it right after? I think it only really matters if for some reason, like, let's say you have like a read miss, right? If you had a read and miss, um, like for example, in this one right here, right, the first line of code, and then like the next line of code, if it was instead of processor 2, it was processor 1, then we don't update the main memory yet. We change this from exclusive to modified instead, and then we update this to 8. And then main memory wouldn't have been updated yet. This would have still been a 5. I think that's the difference. The modified state is if it's already in the cache, I think.
I do have a question right now. In instruction 5, why do we have invalid as a state, the initial state?
You mean for
Yeah.
this and this?
hmm
Yeah, so processor 2 is doing a S-type instruction, right? It's storing new data, right? But right now, these two caches have a certain value, right? And then
hmm
we're saying, okay, we're gonna write to this address a new value. So when we write it, um, these two caches will snoop the fact that it's like trying to write. Um, and then it's gonna have to be invalidated because uh, this isn't really up to date anymore, right? Because you see it's an 8 here, but like once we do the S-type instruction after it's done, there's a 9 in the main memory.
Oh, okay, that makes sense. Okay, I see.
Yeah,
Mm.
so it's because processor 2 is changing the value at address X, so that means that like whatever the other caches have is bad. So when processor 2 does the store instruction, I think he said that it has to send something on the bus, basically an invalidation bit like to tell when the other caches snoop, it'll see like, oh, processor 2 is doing a write. We have whatever it's writing to in our cache, so we have to invalidate that.
hmm Thanks.
Yeah. 3 processors again. Messy. Hmm. This is write to and allocate, but um, oh, it's gonna be similar, I think. Um, definitely the load, right? Main memory has a 5, like he told us. Initial. Um, so this will be a read, just a regular cache miss, right? A read miss. So we'll bring it to the cache. It'll be exclusive. It'll have a 5. And then processor 2 is going to try to do a write. And then it's not going to be in the cache. But it's do not allocate, so we don't need to bring it. We have to update the cache. Wait, no, we update the cache when we update the... Okay, so we only update the cache if it's in the cache, right? But since it's not in the cache, then we have to look at if it's allocate or do not allocate. Since it's do not allocate, we won't bring it to the cache, and we'll just update it straight. But then when we update it, cache 1 has it, so it has to be invalidated. So I think it's invalidated with a 5, and then main memory becomes an 8, just like the other with write back. And then processor 3 is gonna try to bring the data. It's a cache miss on read, so bring it. No, the other caches will snoop, but there's nothing. Nothing has it, so it's exclusive. 8. This is still an 8. And then processor 1 will also try to read it, but then cache 2 will snoop and just drop it on the bus for it, and it will set its state to shared. And same thing here, since I got it from there, cache shared. And then the last line, I think it's literally exactly the same, right? Because they won't be in the cache. That's fine. It's do not allocate on write miss. So it won't have to read it. So just write directly. And then this will be updated. But before these get updated, these have to be invalidated. And then this becomes a 9. I think it's literally the same for these lines of code. That was what?
Yeah, I think it was 6.
Yeah, 6.
Oh, no, 7? Oh, my bad.
I think it was 6, right? Yeah, I think it was 6. I kind of get the answer for that one.
Oh, wait, this is both 6 and 7.
Yeah, this is exactly the same, right? 5, 8. Yeah, for this one, it's exactly the same. Okay, and then problem set 7 is going to be allocate. So I think it changes for this, right? Okay, this is right through an allocate. So main memory has 5 initially. We load it. There's a miss, so we bring it to the cache of a processor 1 or cache 1. The state's going to be exclusive and 5. Okay. So now this is an S-type instruction on line 2. There's going to be a write miss. So this time it's allocate. So then we have to read and bring it to the cache, basically, right? For cache 2. When we try to read, the other caches will snoop. So then this will become from E to S temporarily, right? Because it'll bring 5, right? But then immediately after that, it'll write it. So then this becomes invalid. And then this will be changed to an 8. And it'll be exclusive now, right? And then this will become 8 in main memory. I think that's what happens, right? Because on allocate, you're basically reading, but then that means the other caches will snoop, and then it'll give it to the cache 2, but then immediately it'll be invalidated since you're writing now. And then this will just be exclusive because you just updated it and no one else has it. So then processor 3 has to read, and then the other caches snoop. Cache 1 has an invalid, so don't care. Cache 2, that does have it, So then it'll share it with it when it snoops. So this will be 8. It'll be shared and 8, I think. And then processor 1 is going to read. So then the same thing happens again, shared and 8. And now processor 2 tries to write. And then, okay, so now this time it is in the cache, so it's right through. So update the cache and update the main memory. So it'll update it, but then it has to send the invalidation bit for this, right? So this goes from S to I with an 8, I think. And then this will become exclusive with a 9. So you have to update the cache and update the memory. Yeah, okay. 5. S to I, 5. S to E, 8. 8. S8, S8, 8. Then they're all sharing it together. And then, yeah, they'll invalidate everything else. Okay. That makes sense. Do you guys follow? Or
Yeah, that made sense to me. Everything's pretty good.
yeah, so you just have to check. You have to make sure like all the other caches when you have to like snoop, and then
Hmm.
if they have it, they share it. But sometimes when it shares it, it immediately gets modified anyway. So then you have like multiple stages happen from one line of code. I think in this solution it only writes
Um,
the final state. Hmm.
can you explain for the second line why did it become shared first?
So we have a allocate on write miss. You see on the last thing. So when you have an allocate on write miss, you have to read the data and bring it to the cache first. So like for problem set 6 that we just did before, it was do not allocate. So that means that when you have a write miss, we don't care. We don't bring it to the cache. For problem set 7, it's allocate on write miss. So when we do have a write miss here, because um, it wasn't in processor 2's cache initially. This was like empty, right? Like over here, there's nothing in the cache. So now it says, okay, allocate on write miss. So bring the thing to the cache. To bring it, you have to read. So that's just reading, and then that means that the other caches will snoop when you try to do the allocation. So if you remember, this had um, valid data in its cache. So when it snoops, it'll give it to it. So that's why it becomes shared and shared. But then right after you read, you still have to do the write. So when you do the write, you're gonna update this from 5 to 8 because that's what the instruction says, right? But then when you do a write, you have to tell all the other caches that, hey, the data you have is invalid. So this goes from shared to invalid, and then you update main memory too. So that's why it's like that.
Okay, got it. Thank you.
Mhm. Um, right, so these are the same thing, except it's right back this time. So main memory has 5. It'll read it just like the other one. Processor 1. The content is 5. Exclusive at the beginning. Okay, so this will be a write miss because it's not in processor 2's cache. Write back and allocate on write miss. So there's a write miss. So you have to allocate We have to read it. So we do snooping. This becomes shared in 5. And it'll share it with this. No, actually, it's shared in 5. This will also share it. Okay, so we allocate it now. And then we have to do actual writing. But it's write back policy. So we only update the cache. We don't update main memory yet. So we'll update this to an 8, which will invalidate this. And then this will become exclusive. But main memory still has a 5 because it's write back policy. And we only update the main memory if we need to. So then, oh, this is an exclusive. Sorry, I said exclusive, right? This should be modified. My bad. It's modified because this cache has newer data than main memory because of the write back policy. So then processor 3 is going to do a read. The other caches will snoop. And then this one has modified data. So that means we have to flush it to main memory first, right? So when we flush it, does it do a write? Or do we just say, okay, main memory has an 8 now, and then this becomes exclusive? Is that what happens? I think that's what happens. And then now the flush has happened. So then when it tries to read it, this cache has good data, so it can go from exclusive to shared. It'll share it with this, and this will have an 8. And then I think processor 1, it'll read it as well. So this will stay the same. And then this one, either of these caches can share. It doesn't really matter who. So it'll share with an 8, and now they're all sharing it. Okay, and then finally, processor 2 is going to do a write, but it's write back policy. So you update the cache, but you don't update main memory. So this will go from S to modified. This will turn into a 9. But when it's doing that, it has to send an invalidation to the other caches. So this will be invalidated, and this will be invalidated. And then the cache is updated, but not main memory. So this stays as an 8. I think that's right. Right? Shared 8.
Yeah, look good.
Yeah. Okay. So that's what happens. Does anyone have any questions? Messi kind of sucks. So
What I'm kind of getting is like modified. We only get the modified bit on allocate on write miss.
we only get the modified allocate this. Uh Well, if you have write through, I think you never have modified, right?
Mm-hmm. Yeah, because it does both at the same time.
Yeah, it does both at the same time. Modified is only for write back because
sometimes the cache and the main memory will have a mismatch.
Mhm.
But then you're asking like, oh, what happens on allocate versus do not allocate, right?
Oh no, I'm not asking. I'm just saying like a statement.
Is there any situation where you could have write back, do not allocate, modified, you're saying, right? Can there be? Because, no, you can, right? Because you can have do not allocate on write miss, but you can still have misses on reads, and then it'll still bring it to the cache, right? And then if you have a write back policy, it will be in the cache because on reads you always bring it to the cache. So you could have modified state even with do not allocate on
Mm,
write back.
I see.
He just didn't have a situation where we read it and then tried writing on the same processor right after that or something like that. You know what I mean?
Yeah, I see. Like, yeah. Okay.
But yeah, for write through, you never have modified state really. And the shared state is kind of who cares as well, I think, right? Well, I guess it does matter. Shared state still matters on write through because when you do a write, you have to invalidate the other one. Okay, so there's one more problem set. I'm kind of tired after this, so I guess we can do like the exam stuff like either tomorrow or whatever day works for everybody.
Yeah, it's pretty late.
Yeah,
It's going on for
so
2 hours now.
yeah, so I guess I'll finish with problem set 8 and we can figure out a time for the exam questions. The
But this
cache
is one we did in
covariance.
class, right?
Uh, I forget if you did problem set 7 or 8.
I think it was 8,
Did you do
yeah.
this?
Because I had the paper.
Oh, okay. I wasn't really paying attention. The cache system messy. Direct map, right back. Do not allocate on right miss. Okay. This is like basically he brought every fucking thing together into one question, right? So direct mapping, right back, do not allocate. Rx equals 1, right? Didn't say anything about memory. Um, okay. So the first line of code is a S-type instruction, right? On processor 2. Do we have address 4 in the cache? No, we don't. It's do not allocate, so we won't bring it to the cache. So I don't think anything changes, right, for the states in that case. This can all stay the same basically. Honestly, just whatever. And processor won't be touched in that case either. Right? Actually no. You have to check if okay. So processor 1 did have it, but it's invalid, so that's fine. So this also doesn't get touched. And then we can update address 4. The data becomes whatever was in R1. Do I know what's in R1? Oh, just R1, right? Because all of the registers have values of 1. So this becomes a 1. This is after this instruction. And then second instruction
writing to address 8 on processor 1. It doesn't have it, so do not allocate on it, so we don't have to read it. But processor 2 does have it, and it's modified. So we have to flush it. So address 8 becomes 17. But then we're immediately going to write a 1, right? Is that what happens? You have it written, right? You have like the solutions.
Yeah, but it's supposed to be posted. Is there no solution sheet on there?
Right.
Yeah, he gave me the exact same thing.
Yeah, okay. So it becomes 17 because processor 2 had to flush the modified data, and then it
Mhm.
immediately becomes a 1 after that. Okay, so that's right. Mm, So then this becomes invalid, right? Well, this is still address 8, but this will become invalid with 17, and the rest stays the same, I think. Another fucking store. Processor 2 for address 3 is invalid. Okay. Yeah, the address is there, but it's invalid, so we don't allocate on write miss. Does the other cache have it? Okay, it does. So it's the same thing. We have to flush the 14 here. So that's on address 3 becomes 14, and then it's going to become a 1 because that's what's in the register. And then this is invalidated with the 14 still for address 3. I should probably write down the rest, right? 2, 5, ME, 3, 8, 9. This one was 8, Y, 7, 5, 6, 3, E, 2, 4. This is a read for processor 1, address 7. It's a read miss. It's direct mapping. Okay. So 7 mod 4, which is 3. Okay. That's fine because cache location 3 has invalid data. So address is now 7. Oh yeah, because the other processor didn't have it. It's this will be exclusive, and this will have 1, right? Wait, no. Address 7 had a 2. Oops. Huh.
This will stay the same. Oh, okay. Address 1 is not in the cache. Do not allocate. Same thing again. There's when it snoops, there's this, so it has to flush this. So address 1, 8 becomes an 8. I don't even know what line of code that is. But it goes from 8, and then it's going to go to a 1. We didn't put anything in register 3, right? Yeah, okay. Yeah. So it'll go from 8 to 1. And then this will become invalid. And there should be 4 still. 2, 3, 5, E. This should still be the same. Okay. I think that's it, right? Is that what it was? Yeah. 17, 1, 14, 1, 8 to 1. Oh, did I copy it wrong? I copied it wrong, didn't I? Whoops. This last line should be 7, exclusive and 2. Yeah, okay. Then 0, 8, 5, 6, 3. Yeah, okay. Okay. Does snooping happen when you're reading? Snooping happens whenever you're doing reading or writing. Basically, anytime you use the bus, the other caches can snoop, because what you have is like your computer, right? And then let's say there's like each of these are like a processor, and they have like their cache on it. But then all of these are connected via the bus, which is just basically wires. And then you can say like, let's say like this is main memory. So this is like C1, C2, C3, C4. You know, this is processor 1, processor 2, processor 3, and processor 4. So since like everything is connected via this, whenever you want to send data to main memory, on here, like all these other ones can see what's on this wire. It's because like if you remember, like each of these has like each of these processors has like MAR, MDR, and like control, and those things are like the registers that communicate through this wire. So when it snoops, like it can put whatever's like this value is onto the wire and give it to it directly instead of having to go to main memory directly. But that can happen for when it's reading data from main memory, or if it's writing data to main memory. So when I was talking about like invalidation bits, it's like, okay, I'm about to do a write to main memory, but these other ones, these other caches will snoop and see like, oh, there's a write going on, and I have it in my cache, so I need to invalidate it. Okay. Does anyone have any other questions before we call it a night?
I think I'm good.
Okay, cool. Right, so let me start the